Welcome grade 10s. This is what I'm calling video 4. It's going to be on interference, and it's the first of 2 videos that you guys are going to get this week. So Dr. Thornton's already spoke to you about properties of waves. Now I'm going to show you destructive and constructive interference. So I'm going to just talk about this paragraph over here first before we do the top paragraph. So interference is when we've got 2 or more pulses that interact with each other in the same space and at the same time. Same space and at the same time. Okay, so if we've got 2 pulses that are crossing, so by that I mean one going to the right and one going to the left, for example, each pulse carries on unchanged in its original direction of motion. Okay, so what I mean by that is if you've got a pulse, here's a red pulse, the red pulse is moving to the right, and I've got a blue pulse, and the blue pulse is moving to the left. So if I've got those 2 pulses, when they pass each other, you're actually going to get one wave that's bigger than each individual. So we've still got that red one moving to the right, and the blue one moving to the left. And as they pass each other, you form one wave that's a combination of the 2. And afterwards, you're still going to have the red one moving to the right, unchanged, and the blue one moving to the left, unchanged, and at their original amplitude. So by that I mean whatever its amplitude was before the interference, it'll have exactly the same amplitude after its interference. Okay. Notice that in the middle diagram here, they were interacting at the same time. Over here, they were acting at the same time. Okay, so interference is when we've got 2 or more pulses that interact with each other in the same space at the same time, and after the pulses have crossed, each pulse carries on unchanged in its original direction of motion. So that's what's happening in this diagram that I've just spoken to you guys about. Okay. The word superposition means placed on top of each other. So we said that the waves superimpose. We can understand what happens when pulses cross by having a picture in our minds of the pulses on top of each other when they cross. So please, this is really important. This is what definition basically of superposition. The principle of superposition posits that where pulses cross, the combined disturbance at any point is equal to the sum of the disturbances. So you add them up. So please make sure you highlight that in your notes. Okay, let's go back to the top of the page. So interference. What do you think would happen if 2 transverse pulses approach each other along a slinky spring? If their disturbances are both the same side and the same amplitude. So I want you to go to the waves, the PhET wave simulator. I did provide the link last week. So if you just Google PhET wave simulator, this will come up, and you can click on play or click on download, and it will open up for you. Alright, so I want you to set it so that you've got a pulse. So on the top left box, you can select pulse, and I'd like you to leave the amplitude as 0.75. Pulse width, that can stay. Please turn down the damping. There's a slider on the bottom for damping, and tension you can make medium. So if I send a pulse and we've got a loose end, notice how the wave does not get reflected. So if the pulse approaches the pole on the right above the equilibrium position, it gets reflected, but it's still above the equilibrium line. Whereas if I change the end to be a fixed end that can't move, notice how the pulse is reflected. So here the pulse is moving towards a fixed end above the equilibrium, gets reflected and goes backwards below the equilibrium line. I'm going to set the end to be a loose end. And when I've got a pulse coming that gets reflected coming back, I'm going to create another pulse. You create a pulse by tapping on that button. Now I'm going to click on slow motion. What you've just seen is destructive interference. I'm going to start again. show you constructive interference. Okay. So we've got two pulses above the equilibrium position, and now they're coming towards each other. The left pulse is moving to the right, and the pulse that's on the right is moving to the left. So select slow motion. Now notice how the waves are starting to superimpose on each other. Notice how you get one big wave that's actually twice as high as each individual wave. So each individual wave's got an amplitude of 0.75. If I were to click on ruler and add a ruler to this, where's 0? There we go. Let's put 0 on the equilibrium point. So this wave is 1.1 centimeters tall. So now it's almost 1.2. 1.2 centimeters tall. And afterwards, notice how each individual wave is 0.7, 0.75. Basically what I'm trying to show you guys is if you add up the amplitude of this wave and the amplitude of this wave, you'll get the amplitude when they are superimposed on each other. And we call that superimposition constructive interference. So they construct, build up to give one bigger wave, with the amplitude equal to the sum of each individual wave. Let's have a look at how this happens on the bottom. So measure that. Notice how that value is half of the amplitude when the waves combine. Okay, so that is constructive interference. So we say that the crests double when they meet, when the two waves meet, and then return to the same size after they've passed. After, that's a very weird looking after they pass. They meaning the waves. Okay, so constructive and destructive interference. When the pulses interfere, the direction of the disturbances must be taken into account. Superposition leads to a larger amplitude, as in figure 1. Larger amplitude, and a smaller amplitude in figure 2. Smaller amplitude is in figure 2. So the larger amplitude we say is constructive interference. Construct means to build up, make bigger. Whereas to make a smaller amplitude, you have to have destructive interference. To destruct. Okay, so either you can have a bigger wave above your equilibrium point or below, just like I've shown you in the FET circuit simulator over here. Okay, so there both waves are above. You get one big wave above the equilibrium position. Or if both waves pass each other below the equilibrium position, you also get one big wave below the equilibrium point. Okay, so that is what's happening over here. Either both combine and you get a bigger wave above, or both combine and you get a bigger wave below. Okay. So if the disturbances are in opposite directions, we say that one's positive and one's negative. When you add a positive and a negative number, the size gets smaller. So by that, I can show you what I mean now. Let's do positive in red. So positive meaning above the x-axis. Okay, so there's a positive wave. Negative meaning below the x-axis or below the equilibrium position. And when those two waves pass, if the red one's moving to the right, the blue one's moving to the left, when they pass each other, you subtract what's above from what's below. So if this wave had an amplitude of 1 unit, and this one had an amplitude of 1 unit, because this one, the red one's above, the blue one's below, it should not come as a surprise to you that 1 plus negative 1, or if you add them together, 1 minus 1 will give us 0. And that's what you're seeing over here, is when the waves pass each other, there's no net amplitude. Sorry, that's what you're seeing over here. Over here, they combine and flatten out. That's why this red is actually done as a dashed line, and the blue is done as a dashed line, so that that's where they would be. But because they cancel out, you just get one flat line. This diagram on the bottom is what happens afterwards. So afterwards, the red continues as it was going. So there's your red, it continues as it was before the interference, and the blue continues as it was before the interference. Okay. Same applies over here, it's just that this red one is a lot taller than the blue one. So suppose that the amplitude of this red wave was 2 units, and the amplitude of the blue wave was 1 unit. 2 minus 1 would still give us a net value of 1, because the red one here is bigger than the blue one. So you've got more on the top than on the bottom. So this is when the pulses interfere, that's your net result. And afterwards, the waves carry on as they were. Red one carries on moving to the right above the equilibrium position. Blue one carries on moving to the left below the equilibrium position. Okay. When the crest of one pulse coincides with the crest of another pulse on the same side of that rest position, the pulses reinforce each other. The amplitude of the disturbance is equal to the sum, meaning you add them up, of the amplitudes of the individual waves. This is known as constructive interference. And when the crest of one pulse coincides with the trough of another pulse, the pulses tend to cancel each other out. The amplitudes, when they cancel each other out, the amplitudes of the disturbance is equal to the difference of the amplitudes of the individual waves. And that's known as destructive interference. When the amplitudes cancel each other out entirely or completely, it's known as total destructive interference. The same thing would happen when two waves overlap completely. You'll get constructive interference, but when you've got a wave above and a wave below, then you can have total destructive interference. And that's what's shown in this diagram here. So you can indicate then that that is total. Total destructive interference, whereas this is not total, it's only partial destructive interference. Okay, let's have a look back at this FET simulator again. Right, so here we've got two waves approaching each other. We've got a wave on the left above the equilibrium position, one on the right below, and I'm going to put it in slow motion. Watch what happens as they approach each other. Just get one net flat line, so total destructive interference. We're going to get constructive interference now. And here we've got destructive interference once again. Notice how after the waves have total destructive interference, they carry on as they were. Okay. One other thing I want you to notice, if I send a pulse, I explained to you again, pulse with a fixed end versus a loose end, and of course no end is that will just go out the window. Alright, so two transverse pulses approach each other on a helical spring. If they are 10 centimeters and 5 centimeters respectively, and they're on the same side of the spring, what will happen? You're going to get a bigger amplitude, and you add up the two values. So 10 and 5 will give us 15 centimeters. I'm going to get a bigger wave, we call that constructive, because they're on the same side. Constructive interference, the amplitude will be 15 centimeters. Okay, if they're still 10 and 5 centimeters, but now they're on opposite sides, you're going to get destructive interference. So you're going to get a smaller wave, or destructive interference. It's a smaller wave, a smaller amplitude. Which will then be 10 minus 5 to give us 5 centimeters. If they were both 10 centimeters and on opposite sides, what would happen when they meet? 10 minus 10 would give us 0, so total destructive interference. So plus 10 plus the negative 10 because they're on opposite sides will equal 0 centimeters. Alright, there was a video that I included on ripple tanks. I'm going to quickly show you that. So again, download the FET circuit, the FET sound and waves. Click on wave interference for the ripple tank. Now, while I'm waiting for it to download, I would like you to picture if you and a friend were both sitting by a pond and both of you dropped a pebble into the pond, you'd get a circular wave emanating from that. So if the waves met and coincided and both of the wavefronts were above the surface of the water, you'd get one big wave. Whereas if you had one wave slightly above and one wave slightly below the normal surface of the water, then you'd get a smaller wave where they would cancel each other out. So you can also have constructive and destructive interference. So click on interference. So you've got various options. You've got a tap dripping, you've got a speaker, and you've got light. You can do it with others if you want to. I'm going to use the tap dripping because I was talking about water in a pond. Please separate them as much as possible, then it will show up better. And let's click on. Let's turn them both on. Okay, so I've turned on the bottom tab. I'd like the top tab to turn on as well. Now notice how the blue represents crests, or whether the water surface is above the ordinary, the waves are above the surface of the water. And where you get a ring from the top tap and a ring from the lower tap coinciding, then we're actually going to get constructive interference and we're going to get a bigger wave. If you're talking about it in terms of sound, let's increase the separation of these two speakers. Make them both create a sound wave. When the sound waves from both combine, so wherever you're getting two black patches, that's where you've got constructive interference. When you've got opposites, so say for example one black and one white, then it's like a crest and a trough, and you've got destructive interference. Okay, so that's what we were talking about with the ripple tank on the bottom of page 16. The wave that I did include a little video on ripple tanks for you. Alright, I would like you guys to please complete the rest of this booklet, and once you're done, then you can watch the rest of the videos. If there's any specific problems that you are encountering, then you're welcome to message me and I will help you. So please, up to and including page 24 is for your homework, and then once you've done that, then you can watch the next videos. Alternatively, I will just put up the memos onto Teams, and then you can message me privately and I'll have a chat to you privately on any difficulties that you encounter. If a lot of people ask for help with the same question, then I'll do another video with just that question. Thanks, Gr10s. Bye.